break and was able to be home at such.
Okay, it's 9 o'clock, so let's get started. We were talking last time about functions, and specifically we had come up with a series of functions that we're going to build on, and I hope you'll commit to memory. We talked about some power functions, x squared, x cubed, square root of x. We talked about some trigonometric functions. We talked about exponential functions, absolute value functions. There's really only one more basic kind of function I want to talk about, and that's the logarithmic function. So let's say y equals the natural log of x. We'll take a look at the basic shape of this thing. So y equals the natural log of x. So remember, the e to the x curve looks like this. Y equals e to the x approaches the negative x-axis asymptotically. It crosses the y-axis at height 1. It increases rather quickly to the right. One second. Excuse me. The logarithm, excuse me, the natural log curve is just the inverse of this function. And an inverse of a function is the graph of the inverse of a function is the original function reflected over the line y equals x. So if we imagine y equals x as a mirror, and we reflect e to the x over that line, we end up with a curve. Instead of approaching the negative x-axis asymptotically, it approaches the negative y-axis asymptotically. Instead of crossing the y-axis at 1, it crosses the x-axis at 1, and it looks a lot like this. And the curve y equals natural log 2, equals the log base 2 of x, log base 3 of x. So note y equals log base 2 of x, y equals log base 10 of x, and y equals log really base any a of x so long as a is greater than 1 looks very similar. So it has the same general shape. Okay, I want to talk a little bit about finding natural domain. Or sometimes we leave the word natural out. Find a domain for a function. So we recall that the domain is a set of values which can go in. Set of possible inputs. So when we're finding a natural domain for something, we're basically taking a formula, a function, and excluding things that we couldn't possibly put in there. So for example, let's start with find a natural domain. Find a natural domain. Let's start with this. F of x equals 1 over x. What's the only number I can't plug in for x?
0.
Yeah, exactly, 0. So we can plug anything in except 0. And so you could write this out any way you want. You could say any real number except 0 in words. You could write it like this. You could say all real numbers except for 0, all real numbers, set minus 0. We learned that set minus symbol the very first day of class. You could write negative infinity all the way up to 0, but don't include the 0. You could, and then 0 to plus infinity. So here we have all the negative numbers. Here we have all the positive numbers. The only thing we've left out is 0. You could do it on a number line. You don't have to do them all. Any one would be fine. So you could put an open circle at 0 and color in everything to the left and to the right and to the left. However you want to write your answer is fine. Here we go. Okay. So let's do another one. How about g of x equals, well, let's just do another one very similar to that. How about we have 1 over x minus 2. What's the only thing I can't plug into that?
2.
Right, 2. If I plug 2 in, I have 2 minus 2 on the bottom, and that's 0 on the bottom. So I have all real numbers except for 2. Let's do one that's a little bit more interesting. What over x squared minus 4? This is very similar to A and B. We don't want the denominator to be 0. So we're going to exclude things where the denominator equals 0. So if I take
2.
minus 4 instead of equal to 0, I know that factors x minus 2, x plus 2 is equal to 0. So x plus 2 or x equals minus 2. So these are the things I want to exclude. This is not my answer. My answer is going to be everything except those two things. I could write it all real numbers except for 2 and negative 2. Notice I put the 2 and minus 2 in braces. I haven't tried to write it like an interval. I could write, well, I don't know how else we want to write this. I could write all real numbers in words. Set 2 and minus 2. I could write negative infinity all the way up to minus 2, and everything between minus 2 and 2 I could write, and then everything from 2 plus infinity. However you want to write your answer. let's do another one. How about we have that. F of x equals the square root of x squared minus 2. If I'm taking the square root of something, what has to be true about the something? What is it okay to take the square root of? Or equivalently, what is it not okay to take the square root of?
Negative number.
Yeah, I can't take the square root of a negative number. I can take the square root of 0, and I can take the square root of a positive number, but not a negative number. So really, if I'm expected to find the domain of this, really what I'm looking for is x squared minus 2 is greater than or equal to 0. If I'm supposed to find the domain of this, it's really an inequality in disguise. I want the thing underneath the square root to be positive. But we've done this before. Let me give this thing a name. Let me call it, I don't know, m of x. I've already called this f, so I'm not going to use that again. I'll just say m of x. And let's do a sign chart for m. Let's factor this as, well, I guess it doesn't factor all that nicely. I guess it sort of factors nicely as x minus the square root of 2 times x plus the square root of 2. That's supposed to be greater than or equal to 0. Or you could use the quadratic formula on it, but that sort of factors. And so those are the two places it's equal to 0. So square root of 2 is about 1.4. We have a 0 there. We have a 0 at minus the square root of 2. That breaks the real line up into 3 parts. I can plug a point into each part. If I plug in, say, minus 2, I end up with minus 2 squared minus 2. That's 4 minus 2, 2. It's positive here. I plug in 0, minus 2. It's negative everywhere in here. And if I plug in a number to the right of root 2, how about 2? I end up with 2 again. That's positive. This tells me I'm looking for my plus signs and zeros, greater than or equal to 0, the plus signs and the zeros. Well, I see plus signs and zeros to the left of negative root 2, so negative infinity all the way up to negative root 2. I also see more plus signs to the right of positive root 2. Oh, sorry, I need to include the minus root 2 because I'm allowed to include the 0. It is totally okay to take the square root of 0. Square root of 0 is just 0. So everywhere starting at root 2 and going to infinity. So if you're supposed to find the natural domain of a function that's underneath a radical, underneath the square root symbol, just set as your very first line of your solution, just set what's under the radical to be positive. How about this? This question looks very similar to the last one. I have the x squared minus 2 under a radical. So I know x squared minus 2 has to be greater than or equal to 0 this time. Could x squared minus 2 be 0 this time? Could it be 0? No, it can't be 0 because I don't have the square root of 0 in the denominator. And so I would have 0, the division by 0. So this time, x squared minus 2 is not only not negative. It's not only greater than or equal to 0, it is definitely greater than 0. It can't be 0 either. We've already done all the work. We have the sign chart we need for this on the blackboard already. This time, instead of looking for the plus signs and the zeros, because I had a greater than or equal to 0, I'm just looking for the plus signs. It's just greater than 0. So it's almost the same answer, negative infinity, all the way up to minus root 2. But this time, I don't include the minus root 2, nor do I include the root 2. Because I don't want division by 0. How about this? Natural log of x plus 3. If you can remember what that natural log curve looks like, so remember what the natural log curve looks like. It's in your notes. We just had it a few minutes ago. It looks like this. Crosses the x-axis at 1, approaches the negative y-axis asymptotically, and grows ever more slowly as we move off to the right. Though it goes up forever, it just goes up less and less steeply. So looking at this picture, you can basically see the domain of the original function y equals the natural log of x. The domain are all the x values where there's a piece of the function. There's no function to the left of 0. So less than 0 is not part of the domain. There is a function, there is curve everywhere to the right of 0, and the curve never touches the y-axis. Curve never touches the y-axis. So the domain of the original function is 0 to infinity. So you can plug in anything to natural log, which is greater than 0, but you can't plug in 0, and you can't plug in a negative. So you can plug in anything that's greater than 0, but not 0 and not a negative number. So basically what I'm asking you for here, if we're going to take natural log of x plus 3 has to be greater than 0. It has to be a positive number. If I was taking the square root of x plus 3, then x plus 3 could be greater than or equal to 0, but you can't take the natural log of 0. So this is just x is greater than negative 3. So when finding natural log, when finding the natural domain, watch out for the following. Watch out for division by 0. Watch out for square roots of negative numbers. You can't have square roots of negative numbers. Not if you hope to have a real solution anyway. Watch out for logarithms of anything that's positive, that's negative or 0. And one more thing, watch out for physical constraints. And I'll explain that in just a second. So for instance, in number 4, if I say x is the side length of the square. Well, that's a length. It can't be negative. So x has to be at least as big as 0. So sometimes the constraints of the problem tell you that a certain variable can't be in a certain range. Okay. And in terms of this class, that should be sufficient. To find the range of a function, we'll leave the graph. And so I'm going to come back to this after we talk a little bit more about graph. Well, maybe I'll talk about one example now. Let's start off with it. Let me give you one example. Y equals x squared. F of x equals x squared. So, as I said before, the domain of the function is the set of all x values where there's a piece of the curve. Well, there's a piece of the curve at every x value. So the domain, you can see right from the picture, the domain is all real numbers because there's curve at every x value. This parabola gets wider and wider forever, even though we only have a limited amount of space in the blackboard. The range is the set of y values where there's curve. So there's no curve down here. So we don't have any curve for negative y values. The first place we have range is at y equals 0, and then this thing goes all the way up. So the range is anything that's 0 and positive. You can see that in the picture. That's all the range is. So the range is 0. There's a piece of the curve at y equals 0. It's right at the origin. And there's part of the curve everywhere with positive altitude. So there's the range. So if you had a picture in front of you, that would give you a really good idea of what the domain and the range were. We have all sorts of algebraic ways to help us find the domain. We don't really have algebraic ways to help us find the range. I want to talk about inverse functions. So here's the definition. Functions f and g are called inverses of one another. We write g equals f with a superscript -1, or f equals g with a superscript -1. You read this f inverse. That's how you read that. It looks like an exponent, but it's not. It's unfortunate that we use the same notation to mean two different things, but we just do. You have to pick it up by context. So we say functions f and g are called inverses of one another if f and g, f composed with g, is the identity. I'll explain that in a second. And g composed with f is the identity. So to understand this, we have to understand composition. So I'll come back to that in just a few minutes. But I want to talk about combining functions. Actually, you know what? I'm gonna stick something else in before I even get to combining functions. So hold that. We'll come back to that. Let's talk about transformations of functions. Then I'll talk about combining functions. Then we'll talk about that. So transformations of functions are certainly something you did in a pre-calculus course. This is all the stuff about shifting and reflecting, that sort of thing. So when we talk about transformations of functions, oftentimes in high school in your textbook, they have like 17 rules that you're supposed to commit to memory. I'm going to reduce it to 5. So here are the rules. Anything you do to the entire function is a vertical change. Vertical changes move in the expected direction. Anything you do to the entire function is a vertical change, and vertical changes move in the expected direction. Anything you do directly to x is a horizontal change. Horizontal changes are counter to the expected direction. Opposite to the expected direction. Now, 3 short rules. Adding or subtracting a number is a shift. Multiplication by a positive number is a stretch or compression. So adding or subtracting a number is a shift. Multiplication by a positive number is a stretch or compression. And multiplication by -1 is a reflection over one of the axes. Transformations of functions, we have these 5 rules. If you do something to the entire function, it's a vertical change. Vertical changes are in the expected direction. If you do something directed to x, that's a horizontal change. Horizontal changes are backwards to the expected direction. Adding and subtracting numbers is shift. Multiplication by a positive number is a stretch or compression. And multiplication by -1 is a reflection over one of the axes. Let's do some examples. How about we start with the curve y equals the square root of x. So let's do y equals graph y equals the square root of x plus 1, like that, where the plus 1 is outside the square root symbol. We know what y equals the square root of x looks like. Let me put a small picture up here. Y equals the square root of x. It's just a half a parabola on its side, and it includes that point at the origin. So looking at this, the first thing we ask ourselves is, are we adding that 1 to the entire function, or is it directly to the x? Well, sorry, this office is full of chalk dust. We're adding, the plus 1 is outside the square root symbol. We're not adding it directly to the x. We're adding it to the entire function, so we know this is a vertical change. Vertical changes are in the expected direction. Adding and subtracting numbers is a shift, so we're shifting this thing. If it's a vertical change, you would think plus would be up and minus would be down, and that's what happens because vertical changes are in the expected direction. So plus 1 means a vertical shift 1 unit up. So instead of having its end at 0, 0, it has its end at 0, 1. Just the original function shifted up 1 unit. Let's do this. Y equals the square root of x plus 1, like that. This is another shift because I'm still adding or subtracting a number. I'm adding the number 1. So you know it's a shift. This time you ask yourself, is the 1 getting added to the entire function, or is it just getting added to the x? This time it's right next to the x. So it's a horizontal change. We know horizontal changes go backwards to the expected direction. Horizontal changes are backwards to the expected direction. So you'd think plus would mean to the right, but it's actually to the left because horizontal changes are backwards. So I take the original function, y equals the square root of x, and shift it 1 unit to the left. Let's do this. How about y equals the square root of x plus 1 plus 1. I kind of combined what I did in the previous two, right? I have this one which shifts the whole thing up because that one gets added to the entire function. And I have this one which shifts the whole thing to the left. So instead of starting at 0, 0, it's 1 unit to the left and 1 unit up. It starts at -1, 1. That's where the end of this thing is. It has the same shape. Across the y-axis at 2, which we can easily figure out. Actually, let me show you how to find the y-intercept. You always find the y-intercept the same way, just set x equals 0. So if we set x equals 0, we end up with y equals the square root of 0 plus 1 plus 1. 0 plus 1 is 1, square root of 1 is 1, that's 1 plus 1, or 2. Similarly, to find the x-intercept, you set y equals 0. This doesn't have an x-intercept, doesn't touch the x-axis anymore. When you find the y-intercept, just set x equals 0. When you find the x-intercept, just set y equals 0. Nothing to it. So, let me dot in the original curve, y equals the square root of x. That minus sign is in front of the whole function, so we know this is a vertical change. So the points are moving vertically. If the points are moving vertically, we can't be reflecting over the vertical axis, because if I move this point over here, that's a horizontal move. So we're actually moving over the horizontal axis. This is a vertical change. So that point goes there, that point goes down here. So y equals minus the square root of x is actually a reflection over the horizontal axis. It's a vertical change. The points are moving vertically, but it ends up down here. So this is y equals the minus the square root of x. And if I had y equals the square root of minus x, that's I take the original curve and I reflect it this way so the points move horizontally. It looks like that. Now you might be saying to yourself, wait a second, I can't take the square root of a negative number, but if x is negative and you put another minus sign in front of it, that makes it positive. So it's okay to plug in -1, because minus minus 1 is 1. Take the square root of 1, 1, no problem. Let's just do a couple more. I'm going to sketch y equals sine x. So, pi over 2, pi, 2 pi over 2, 2 pi. Remember, those are not the only numbers on the number line. Those are just the places where something interesting happens with sine and cosine. The numbers 1, 2, 3 are still there. wonky, but that's pretty good. So here's the curve y equals sine x. Let's sketch y equals 2 sine x, and also y equals sine 2x. Those are not the same function. Definitely not the same function. So in both cases, I'm multiplying by 2. So I know it's a stretch or a compression. Here I'm multiplying by 2. I'm taking the whole function sine x and multiplying by 2. We know that this is a vertical change. You would think that 2 would be a stretch. It's bigger than 1. 2 is bigger than 1. And vertical changes are in the expected direction. So this really is a stretch. So I'm taking the whole thing and stretching it vertically. Every point gets twice as far away from the x-axis as it was before. Stuff above the x-axis goes up. Stuff below the x-axis goes down. So this point is right on the x-axis. It stays there. This point was 1 unit above. Now it's 2 units above. This point was on the x-axis. This point was 1 unit below. Now it's 2 units below. And this point was right on the x-axis. So the curve y equals 2 sine x has the same period as y equals sine x, but it has twice the amplitude. So this curve is y equals 2 sine x. Amplitude's now 2, but the period is still too high, the time for one complete cycle. For those of you that think in terms of sound waves, in terms of music, these two notes are the same frequency, they're the same note, but this one's louder. Y equals sine 2x, we're taking the 2 and multiplying it directly against the x. We know that this is a horizontal change. Horizontal changes are counter to the intuitive direction. You'd think 2 would be a stretch, but this one's actually a compression. So we're going to take the original curve and smush it. Every point gets half as far away from the y-axis as it was before. This point's right on the y-axis. This point was at pi over 2. Now it's at pi over 4, but same height. This point was at pi. It's half as far away now, at pi over 2. This point at 3 pi over 2, half as far away. That's 3 pi over 4. It's still down at height minus 1. And this point at 2 pi is still here. So we've taken this whole original curve and smushed it. Not the stretched curve, just the original curve. And we could keep going if we wanted, but this curve oscillates twice as fast. So this is the curve y equals sine 2x. It's a horizontal smush. It's the same loudness as the original curve, but it's oscillating twice as fast. For those of you that think musically, it's 1 octave higher. Okay. I think that's it for now in terms of transformations of functions. Let's talk about combining functions. I could take two curves and add, subtract, multiply, or divide them. We can combine them with addition, subtraction, multiplication, and division. This is an easy thing to do. So for instance, if f of x is just the function, say, x squared, g of x, let's say, is the function sine x, I mean, the easiest thing you learn, then f plus g of x, just take your first function, take your second function, put a plus sign. If I wrote f minus g of x, you put a minus sign in it. If I wrote f times g of x, multiply them, and if I divided them, do the division. That's all there is to it. You can take two curves and add, subtract, multiply, or divide them. I want to look at an example just briefly, because this is something, at least with addition and subtraction, that's pretty intuitive. Let's say I had f of x equals x, and g of x equals sine x. You know what the curve y equals x looks like. It's just a straight line going uphill at 45 degrees. And you know what the sine x curve looks like. It just oscillates up and down. So here's y equals x, y equals sine x looks like this. If I want a graph of y equals x plus sine x, just taking these two and adding them, you might be able to guess exactly what it looks like. You can see its parentage. When you add two functions, all you're doing is adding the y values. So at this x value, you take that y value and add it to this y value, and you end up somewhere up here. So let's see. Let me just draw in some reference lines for myself. So y equals x plus sine x looks a lot like this. It's just that oscillating function going uphill to the right. And looking at that function, you can kind of see its parents. You can see that it goes up to the right just like y equals x does. And you can see that it oscillates just like y equals sine x does. It has both features. When you take two functions and add them, you can see the parentage. Oftentimes you can anyway. In this case, you certainly can. We can also combine functions via composition. Also combine functions by composition. You might remember this, f, little circle, g, f composed with g of x. Sometimes we sort of jokingly refer to that as fog. That's just really a shorthand notation for f, g of x in parentheses. So if you remember, I thought of functions as machines. What you're doing is you're taking two machines and putting them in parallel. You start off with x, it goes into this first machine. The first thing that you do to x is g. And what pops out is g of x. Then you put that into f. This is the f machine. And what pops out is f of g of x. So it's two machines acting in series. So when I was a small child, I used to, before I started school, I would run errands with my mom. And one of my favorite errands was going to this bottling plant where we bought soda. And they had all these machines that were acting in parallel. The bottles came out of the dishwasher, and then they went into this one carousel where they each got filled with soda, and then the bottles came off that and went along a conveyor, and they went to another machine which capped the bottles, and then they went through another conveyor and the bottles got put into boxes. So the output for one machine is the input for the next machine. The output from the filling machine is the input for the capping machine. The output from the dishwasher was the input for the filling machine. That's all that's happening here. You have two machines, and they're acting in series. That here we have something going in, it's like empty bottles go into the filling machine, they come out as full bottles. They go into the capping machine, now they're full bottles with caps on top. That's all that you're doing when you're taking the composition of two functions. But I see I'm out of time. Any questions before we go? No? Oh, yes. Yes, there was a question. Robert? No? Oh, never mind. That's not a question. That's just my notes. So I guess there are no questions right now. If you have any, feel free to send me email. Have a good Labor Day, and I will see you all on Wednesday.